In this video, we'll go through the various graphs of a simple pendulum as what you can see here. There are a few things that you need to know about simple pendulum. Let's consider position A and C. You should know that at both positions, the pendulum bob is momentarily at rest, so there's no speed, therefore no KE. And we are going to take the point B as the reference height. That means at the ball at B is the lowest. So there's no height here. So A and C will have the maximum height, maximum GPE, where at B, the lowest point, it will have the highest speed, highest KE, but there's no GPE. And let's take the reference point, the starting point at time equals to 0 when the ball is at B. So you move to the right, come back to B. That's not complete oscillation. It has to go to A and then come back to B. Then that's one complete oscillation. And let's assume, for easy reference, let's assume the period is 4 seconds. So each section is 1 second, 2 second, 3 second, and 4 second. So that means the frequency is 0.25 Hertz. Now let's start with the first graph, which is a displacement time graph. As mentioned, we'll take the reference point as point B here, and right now the ball is at the reference point, so there's no distance, no displacement. And of course, we're going to take the ball moving to the right as positive, so the first position will be over here. Then as the ball moves to the right towards C, the displacement keep on increasing. So at 0.1 second later, that will be the maximum displacement. Okay, we will not give it a value, but you understand that's the maximum. And then at 2 seconds, it is back at to its original position. So once again, the displacement will be 0. And then when it goes to the left side, all right, now because here is 0, to the right is positive, to the left is negative. So as it goes towards the A, okay, the displacement will be negative and it will be maximum. So it's over here, and lastly it goes back to the original position B at time equals to 4 seconds. So the first graph is rather straightforward. You have this shape. Okay, that will be your displacement time graph. Next, let's go to velocity time graph. Now, as mentioned, at point B, the ball is at its fastest speed. So the velocity will be the maximum. Let's put it at here. And then when it reaches C at time equals to 1 second, so the speed, because it's at its highest point, the speed is 0, so that will be the case. And after which, from C is coming back, is moving in the opposite direction, so the velocity will be negative at point B. So this is where it will be at 2 seconds, but it's negative because opposite direction. And as it continues to go to A, that's where the speed goes back to 0 at time equals to 3 seconds. And then finally, it goes back to point B to the right. So the speed will be maximum. So the graph will look like this. What if the question gives you speed, a scalar quantity, instead of velocity time graph? If this is speed, you just know that there's no negative, so you just flip whatever that's at the bottom here over to the top. So that's how the graph will look like. All right. Next, we have the acceleration time graph, and it might be easier to actually just refer to the velocity time graph here. Now you can see that over here at this 2 point, the gradient represents the acceleration, if you can recall. So if you strictly speaking, the gradient here, the tangent here is actually a horizontal line flat with no gradient, so no acceleration here and here. Because if you continue with the graph, all right, this is the position where the tangent, the gradient is over here. So that means the first part here at time goes 0, there's no acceleration. Then as it moves from B to A, if you can see that the speed is decreasing, so it's a deceleration, is negative. So, and another thing here is this, at this point here, the gradient is the maximum at 1 second. So 1 second, the acceleration will be the greatest, but it's negative. So this is where it will be. And then when at 2 seconds, it goes back to your point B. All right. And once again, the gradient is 0. And then at 3 seconds, the acceleration will be the greatest because the gradient here at this point here is the steepest. So it's over here. And lastly, when it goes back to your point B, once again, there's no gradient, there's no acceleration. So the acceleration graph will actually look like this. So if I were to draw the pendulum here, this is your point B, A, and this is your C. So when starting at time equals to 0, the ball is at its fastest, but there's no rate of change of velocity. You can see that, okay, the gradient here is flat. So this is the part where it's 0. And when it's at point C, okay, momentarily is at rest. So the only force acting is your weight, which is your acceleration due to gravity. That's why it's a minus 10 here, and this is a 10. All right. And then when it goes back here, then come back to A, it's the same thing. It's if there's no air resistance, so the acceleration will be 10. And then it goes back to point B, where it's at 4 seconds. Next, for angle time. All right, let's assume the angle here is positive, okay, in this direction. So at time equals to 0 at position B, there's no angle, so I'll be putting a cross here. 1 second later, when it goes to C, the angle will be maximum. And when it goes back to B, it will be 0. Then when it's 3 seconds at position A, this is negative. If the right side is positive, the left hand side will be negative, so negative angle, and lastly goes back to B. So the shape will be as such. Next, let's go to the height time graph. Now from the diagram as mentioned, the at point time equals to 0, B is at its original position and B will be the reference height. There's no height here, so it will be 0. At time equals to 1 second, when it's at point C, the height is the maximum, so that will be the maximum height. Time equals to 2 seconds, it goes back to point B, no height. And then 3 seconds, it will be the highest height from the reference ground, and then go back to B again. So the graph for the height time graph, it will basically look like this. So let's proceed to the gravitational potential energy. The formula, as you know, is mgh. So in other words, is the GPE is directly proportional to the h. So the graph, as you know, will look very similar to the height time graph. So the shape will be exactly the same. All right. And the last one here, KE, as you know, conservation of energy. Energy cannot be created or destroyed, but it can be transferred from one store to another. So in this case, it's between the gravitational potential store and kinetic store, but the total energy of the isolated system remains the same. So in other words, if at time equals 0, the energy GPE here is 0. That means to say the KE will be at its highest point. Another way of seeing it is at point B, as mentioned, is the lowest point. The speed is the highest. The velocity is the highest, and therefore the kinetic energy will be the highest, half mv squared. So it's basically the opposite of GPE. So at time equals to 1 second, which is at the point C, is momentarily at rest. So the speed is 0, KE will be 0. So as mentioned, it will be just the opposite. So the graph will look like this. And that's how you draw for the kinetic time graph. All right. Now, so there we have it, all the graph here, but I really hope you don't memorize the graph because the question can be different, depends on where I set my starting point, the starting position, and where's my reference height, and so on and so forth. So for example, let's use a blue color. Just a example, there are questions where instead of starting at point B, I will start at point A. So that is where time equals to 0 and the displacement will be to the right. So if that's the case, maybe we just draw on the existing graph here using a blue color ink to show you what will be the difference and what are the things you need to take note of. So as mentioned, if A is the reference point, time equals to 0, as it is being released, the displacement keep on increasing and then comes back is decreasing. So there's no negative portion because it's not going to the left of the reference point. So at time equals to 0, when the ball is released, the displacement increases until the maximum at point C. But this displacement previously is from B to C, so the displacement, the maximum is here. But now A to C, you can see that the displacement is actually almost double. So the displacement will be greater. So let's draw on the existing graph here. So time equals 0. At point A, there's no displacement, and as it goes towards B to the C, at time equals to 2 seconds, the displacement will be higher. So let's assume it's here. And then when it goes back to point B and point A will be 4 seconds, that's where there's no displacement. So the graph will look like this at point C and then come back to here. So this is your A, this is your C, and this is back to your A. So your point B is somewhere around here at 1 second and point B is over here at 3 seconds. So the graph, as you can see, is rather different. Next, let's go to your velocity time. And because the ball starts from A, which is the speed is velocity is 0. So at point A, it will be here. And then at point B, okay, the speed is fastest at time equals to 2 seconds. That's at this position, point B. So this will be the graph and you will follow this way. At time 2 seconds, you'll be at point C, momentarily at rest. And then time equals 3 seconds back to your position B. But now since the direction is opposite, it will be negative. And then lastly goes back to A. So the graph will look like this. Okay. Next, let's go to the acceleration time graph. As mentioned previously, it might be easier to just look at the velocity time. And at position A, when you release the ball, the acceleration, the gradient here is the steepest. So the acceleration will be the maximum. So it will start from here. And then at your time equals 1 second, the gradient is 0. So the acceleration will be here. And then 2 seconds will be here. Then 3 seconds. And then 4 seconds here. So the graph will look like this. Now, I won't go through all the graph, but maybe let's finish up the GPE and the KE. As mentioned, it will be opposite, so the graph will just look like this. If I release from A, and A will be my reference point, and of course, your kinetic energy will be flipped. It will be like this. All right. So I hope you get the idea. Really look at where's the reference point, where's the starting point, and then understand the motion before you interpret or you draw the graph. Now, before I end the video, now I want you to take note of another scenario. As you can see, let's say a slotted mass is attached to a spring and you pull it down gently and then let it oscillate up and down. So if taking the base as the reference here, this is the middle position, something like a pendulum. There are 3 positions here. When it oscillate to the highest point, that's the base is over here. So there's position A, B, and C. So once again, if I want you to take note is when this thing is vibrating at position B, the middle here, the speed will be the greatest. Okay, and likewise for point A and point B is at the 2 extreme end of the oscillation, the speed will be 0. So these are things that you need to take note of, and the graph will be slightly different. But I will not go through the video here. You can click on the link in the description to look at this infographic. All right. So I hope this video can help you. Thank you.